The functional group that we will study the most in this chapter are going to be the alcohols. Of course, alcohols have the generic abbreviation ROH, and we can classify alcohols in terms of how many R groups are on the carbon with the hydroxyl group. The simplest alcohol is going to just be methanol. But then if you have a one R group on the carbon, that would be a primary alcohol. 2 R groups would make it a secondary alcohol, and 3 R groups would make it a tertiary alcohol. As far as nomenclature goes, you'll probably need to read through the text for the details, but the major points about naming alcohols is that the parent chain that you choose must contain the carbon that has the hydroxyl group. And then you want to actually number the chain in such a way that the hydroxyl group's on the lowest number possible. And then finally, you put an OL ending at the end of the name to indicate that the species is an alcohol. Alcohols exhibit, of course, dispersion and also dipole-dipole interactions. But alcohols can also exhibit hydrogen bonding. They have an H bond donor and an H bond acceptor. So this hydrogen bonding is going to have consequences on the physical properties of alcohols. As far as boiling point goes, alcohols are going to have much higher boiling points than a similarly sized alkane. So if you compared, say, pentane, which should exhibit about the same amount of dispersion as butanol, you can see drastic differences in the boiling points. The alkane is way down at 36, while the alcohol is up at 118. So that's that hydrogen bonding that's coming into play there. There's a rule that we use for solubility to predict if something's going to be water soluble or not. And it's kind of just a rule of thumb, so it's not set in stone. But for every 5 carbon atoms, you need to have a polar group of some sort to be significantly water soluble. And we can see how that plays out with the alcohol series. If we start with just the smaller alcohols, so 1, 2, and 3 carbons, of course they have the hydroxyl group, which is very polar, and these are all miscible in water. In other words, there's no upper limit to the solubility. But then you hit a point where there is a limit when you get to 4 carbons. And then you can see that number goes down when you get to 5 carbons. It drops drastically. It goes down by a whole decimal place here when you get to 6 carbons. And so this is where that kind of rule comes in. It doesn't mean that the solubility drops to 0 if you only have one polar group for, say, 6 carbons. But it just means that it drops way off. And so we would not consider this to be significantly soluble in water. And then you can see how the trend goes with 7 carbons and then finally with 8. And when we hit octanol, we actually consider this insoluble. It doesn't have a solubility of 0. I mean, you can see what it is here. It's at the 4th decimal place over. But it's very, very sparingly soluble is how we would classify that, and so for all intents and purposes we would call this insoluble in water. We've already learned how to prepare alcohols from alkyl halides by using either hydroxide to do an SN2 substitution or just water to do an SN1 substitution. Let's map out the reactive sites of the alcohol. We have the fairly acidic proton with a pKa of 15 or 16, and we know that we've been able to deprotonate that with a number of bases. But we also have an electrophilic carbon here and a nucleophilic oxygen. As a nucleophile, we have seen a alcohol in an SN1 reaction attack an alkyl halide to give an ether product. Don't forget that there's this proton transfer step at the end whenever you start with a neutral species like this, where this proton is removed. But a much stronger nucleophile is going to be the alkoxide, which is the deprotonated form of the alcohol. So if you subject this alcohol to a base, and the most commonly used one is NaH, where hydride ion is the basic species. and that will drive the reaction all the way to completion. And so you can get the alkoxide, which is a strong nucleophile. Then that nucleophile can attack an alkyl halide via SN2 substitution, also to give an ether product. And this particular reaction has a name. It's called the Williamson ether synthesis. It's really nothing new. You've already seen this in the previous chapters, I think chapter 7, but now we're giving it a name. In this chapter, we're going to look at nucleophilic attack at this electrophilic carbon here.